This section is really a follow-up to section 7.3, where we talked about the idea of a path-independent force. And one way to look at this is to consider the work done going between 2 points. So let's say I've got point R1 here and point R2 over here. And so the work done in moving a particle from one point to the other, if it only depends on the two endpoints, then we can refer to it as a conservative force. So if the work done going between those 2 points only depends on R1 and R2, that's a conservative force. As an example of a force that isn't conservative, if you consider the friction force. All right, so the work done by friction, let's say we've got a block that we start right here and we push it in that direction. The work done does depend on the end points, but it also depends on the direction. So if we push this way, then the work done is going to be negative. The work done by friction is negative. So it depends on the endpoints, but it also depends on the direction, because if we were instead to start right here and move in this direction, we would still have negative work done by friction. If instead of going straight between these two, we took some convoluted path, we could have even more work done. So friction is going to depend on the path you take. Another example of a force that is not conservative is air drag. If you consider taking, say, a big paddle that has a lot of surface area, and consider the work done by the drag force, if we just go back and forth between these 2 points, then we're going to have the same work done no matter which way we go. If, on the other hand, we take some nice convoluted path with our big paddle, we can get a lot of work done by air drag. A good example of a conservative force would be, say, the gravitational potential energy. So if we go between these 2 points, and let's say that this way is up. So really all that matters is the change in height. If we lift this object up against the gravitational force, the work done by gravity is just going to be equal to mg y2 minus y1, where these are the two components. If we do the reverse, if we start at this point and we go back, the work is equal to mg y1 minus y2. So it really, the work done only depends on these two positions. It doesn't depend on the path we take. So this is really what we were driving at with the idea of path independence and conservative forces. And the importance of a conservative force is a conservative force can have a potential energy function associated with it. A non-conservative force doesn't. And so whenever you're dealing with a non-conservative force, it really works best to have that be in your surroundings so you can calculate the work done.